Hey guys, welcome to my channel. Around the world, a wave of massive construction projects is reshaping the future. From California's $130 billion high-speed rail to Saudi Arabia's ambitious Line City. We've been watching these developments for years. But beyond the headlines, other breathtaking mega projects are quietly transforming our planet. Take China's Xiong'an Smart City, for example, a $95 billion investment built from the ground up in just 7 years. Over 3,000 buildings have risen, and the city features digital roads that collect real-time traffic data and calculate optimal emergency routes. These are not just construction projects, they are building the future. China is known for its ancient history and booming economy, but perhaps the most astonishing thing is its incredible speed of construction. While the U.S. high-speed rail faces decades of delay and Saudi's Line City remains largely on paper, China has turned barren land into a futuristic city at breakneck pace. This $95 billion mega project didn't just build skyscrapers, it laid down roads that can think. These smart roads calculate the fastest routes for emergency vehicles automatically. And this is only the beginning. China's ongoing mega projects are redefining the scale of modern infrastructure. So here's the big question. How is China building so fast? And how will these projects shape the global future? Today we explore China's most mind-blowing mega projects that are not only changing cities, but global standards. China has already done what many thought impossible. It's building a $95 billion smart city on the flat plains of Hebei and doing it at breathtaking speed. This is Xiong'an New Area, a second capital hub designed to relieve Beijing of its non-core functions. Spanning over 2,000 square kilometers, the city is planned as a high-tech, green, intelligent, and livable urban space. Unlike traditional cities, Xiong'an was designed from scratch, both above and below ground. Underground, there's a complete transportation and utility system. Above ground, the city emphasizes nature and open green spaces. The infrastructure blends subways, high-speed rail, water systems, power grids, and 5G networks, all into one ecosystem. It's thinking roads, powered by 5G and IoT sensors, monitor traffic in real time, adjust signals dynamically, and can even calculate optimal emergency routes. Imagine a fire truck getting all green lights to reach the scene in record time. That's not science fiction. That's happening now. While other countries debate whether to build, China is already focused on how to build better. This difference may define the race for the future. Next, let's shift our focus to a completed mega project in China. Not just a transportation hub, but what many call the largest high-speed railway station in Asia, Xiong'an Station. This is not just a train station. This is a 60,000-ton steel masterpiece, a mega project where high-speed rail meets futuristic architecture, built not just to transport people, but to showcase the future of infrastructure. Construction began in December 2018. completed by December 2020. In just 2 years, China completed what the world thought was impossible. China's incredible engineering doesn't stop at building cities. It also extends to the movement of water on a national scale. While southern China has abundant water, the north faces chronic shortages. To solve this imbalance, China launched the most ambitious water transfer project in human history, the South to North Water Diversion. With a staggering $120 billion investment, this project spans over 14,000 kilometers, equivalent to building a waterway from Beijing to Egypt. The central route alone crosses the Yellow River and the rugged Taihang Mountains, posing extreme engineering challenges. Hundreds of pumping stations, reservoirs, and tunnels had to be built. And to protect the water source, nearly 400,000 people were relocated. Today, over 10 billion cubic meters of water flow northward each year, bringing vital supply to Beijing, Tianjin, and beyond. This is not just an engineering feat, it's a national lifeline. The South to North Water Diversion Project is the world's largest interbasin water diversion project. It has the world's largest aqueduct system. Transporting water from up high, the longest of them reaches 9 kilometers in one stretch, so that it is not affected by the surface environment. It employs the world's largest pump station group. Designed in 13 cascades, the pump stations lift water stepwise and send water from Yangzhou all the way to the southern bank of the Yellow River. Numerous water interchanges high and low are built. Some cross the Yellow River beneath its riverbed. Some stride the Huaihei River from above. Major rivers that are vastly apart now meet with each other. Thanks to the automated facilities that equip the entire route, this grand project is able to navigate through 8 provinces and a major river basins, diverting water over 2,000 kilometers cumulatively in an orderly manner. 9 years into its full operation, water sufficient to fill up the entire Yellow River has been diverted to North China, meaning that 170 million people in 44 cities now use water from the Yangtze River. Today, empowered by modern technologies, China are reshaping rivers like never before, and even create new rivers on this very ancient land. Beyond water, China is now tackling some of the harshest terrain on Earth with the construction of the Sichuan-Tibet Railway, a mega project across glaciers, earthquake zones, and towering mountains. This 1,959-kilometer railway links Chengdu and Sichuan to Lhasa in Tibet. It crosses 14 active fault lines and numerous snow-covered peaks. Engineers face extreme altitudes, frigid temperatures, avalanches, landslides, and earthquakes, all in one project. Some sections exceed 4,000 meters above sea level. Building a single tunnel can take 5 years or more, but once complete, this railway will cut travel time from 36 hours to just under 13. It's more than a transportation line. It's a symbol of China's determination to push the limits of engineering. And the world is watching as this miracle unfolds. So why can China build these colossal projects in just decades, while many Western countries spend years debating a single subway line? The answer may lie in policy execution, integrated supply chains, and a bold, long-term vision for infrastructure. China doesn't wait until every problem is solved before starting. It starts and solves problems along the way. In China, infrastructure isn't just an economic tool, it's a national strategy. Each rail line, tunnel, and bridge represents a vision for the future. Of course, these projects come with their own challenges, from environmental concerns to resettlement and social equity. But one thing is clear, China is redefining what's possible through action. In the future, global competition may not be just about technology, but about who builds faster, smarter, and with greater resolve. For decades, China's infrastructure development has been nothing short of astonishing. Bridges rise like bamboo shoots after rain, leaping across canyons, spanning vast rivers, and linking regions once divided by nature. They've transformed not only how people travel, but the very geography of the nation. From Chinese roads to Chinese bridges, from colossal tunnels to massive dams, from high-speed rail cities to vast underground networks, China's engineers continue to break world records, one project after another. These national icons power the nation's economy with unstoppable force. The world is still the same world, but China is no longer the China of the past, where there are mountains, roads are carved. Where there are rivers, bridges rise. With courage and mission, Chinese engineers turn the impossible into reality, again and again. At this point, many American viewers might be wondering, is China already a developed country? Then why does the US government still refuse to officially recognize it as such? Why do Western media outlets constantly amplify the China threat narrative? And why do global research reports often rank China as the world's #1 in so many fields? The answer is simple: because China has become powerful, and it did so with astonishing speed. A country once written off as an agricultural backwater is now emerging as a global industrial powerhouse. And that transformation happened in just a few decades. To the world, that's not just growth, it's a shockwave. Seeing China grow stronger and stronger, the United States is starting to panic.
I am stunned to hear some of the rhetoric coming from the other side around a bill that finally, after decades, recognizes that we are in a very stiff competition with China. And for the longest time, America didn't know it. China was in this competition. China was doing everything they could to dump steel in our country. They spend 7 to 9% of their GDP on infrastructure every year. They got islands in the South China Sea. They told us they weren't going to militarize them. Now they have. They have bases in Africa, long-term raw material contracts in African countries to solidify their control of precious metals so that our phones, our weapon systems, our computers, they have a plan. This is not complicated, but it's being seen through the prism of our current broken, insane political system. And so what we're trying to do here is recognize that they're winning. China has a 10-year plan, 50-year plan, 100-year plan. We live in a 24-hour news cycle talking about Dr. Seuss, Big Bird, M&M's, SpongeBob, and we're getting our clock cleaned.
China's strength didn't happen by luck. China's rise is one of the most dramatic national transformations since World War II. It carved roads through mountains and built bridges across rivers. And in that relentless pursuit of progress, China earned a nickname that shook the world: the infrastructure maniac. Demolishing a bridge in just 25 hours, upgrading a major train station overnight. The speed of Chinese infrastructure builds is unmatched and nearly unbelievable. But there's more to it than just speed. China's engineering marvel even made headlines in the UK, where a popular TV show sparked heated debates about the project while using it to roast their own country's notoriously inefficient railway system.
How the Chinese do these things, and I noticed that they were able to build a whole new station in the space of 9 hours by flooding it with thousands of workers. We should be much more imaginative about getting infrastructure in quickly instead of condemning people to being isolated in remote areas.
Mel and I shared a taxi coming here, and the commentary I can tell you in the taxi was that the roads looked better than the area where we were living in England. I'm delighted to hear it, but I have to say to you, it was much better than in Buckinghamshire. But everybody in their own area complains, and the truth is our road repairs have been very, very bad, and it's deteriorating. And yes, austerity has prevented expenditure on all sorts of things that we could need to spend money on. But equally, if we cannot borrow...
China now has over 143,000 kilometers of expressways and 30,000 kilometers of high-speed rail, both world records. From remote villages to booming cities, the entire country is connected by a vast and seamless transportation web. To build that, China had to overcome extreme terrain, geological complexity, and ecological challenges. And it did, again and again. Take the Hong Kong-Zhuhai-Macau bridge, for instance. At 55 kilometers, it's the longest sea-crossing bridge on the planet. Engineers call it the Mount Everest of bridge building. And yet, China built it, under tight constraints with unmatched precision. This isn't just speed, it's engineering power. Behind the nickname infrastructure maniac lies more than just engineering power. It reflects decades of scientific innovation, bold planning, and the will to execute at scale. Each bridge, tunnel, and highway is not just concrete, it's progress. And that progress is meant to serve the people. Infrastructure isn't just about concrete and steel. It carries the hopes of a people, the dreams of a better life. On this ever-advancing journey, China's infrastructure fanatics will keep pushing forward, driving the great vessel of China steadily through the waves of the future. And that future is forcing the world to rethink what infrastructure really means. When you think of infrastructure in the United States, the first things that probably come to mind Are the iconic orange-red cables of the Golden Gate Bridge or the endless stream of cars on the interstate highways? These are, without a doubt, symbols of American pride. After all, the Golden Gate Bridge was completed in 1937, and the Hoover Dam stunned the world way back in the 1930s. But today, let's shift our focus halfway across the globe, to China. There, a groundbreaking infrastructure revolution is unfolding, one that is redefining the scale, the speed, and the technological limits of what we once called engineering marvels. This is the story of China's infrastructure, a story of breathtaking ambition and record-breaking projects, of a nation reshaping its landscape at lightning speed and rewriting the global playbook for what infrastructure can achieve. Can you believe this? While America is still stuck in endless debates just to renovate a single bridge, China has already built the tallest bridge on Earth, suspended between cliffs as high as a 200-story skyscraper. While American high-speed rail proposals are still stuck in Congress, China's bullet trains are racing at 421 kilometers per hour across a staggering 40,000 kilometers of high-speed rail, more than the rest of the entire world combined. This isn't a sci-fi movie. This is real. This is China, redefining what's possible in engineering, one mega project at a time. To be honest, when it comes to infrastructure, the gap between China and the US might be far bigger than you think. Take high-speed rail, for example. America's first high-speed rail project, the California High-Speed Rail, was approved back in 2008. And the result? 16 years later, it's still not finished. The original budget of $33 billion has ballooned to over $128 billion.
So we're here to talk about the California High-Speed Rail Project. So when originally conceived, the voters of California voted in Proposition 1A that they would have a high-speed rail from LA to San Francisco. It was going to be done by 2020, and it was going to cost $33 billion. And people were excited, they were thrilled, take people off the road, out of the air, put them on rail, move them quickly. It was an exciting time, exciting promises for an exciting project. Where are we today? Well, today we are severely, no pun intended, off track. And that project, thus far, is going to cost the California taxpayer and the federal taxpayer, at best estimates, $33 to $35 billion. At best, that portion of the project is not going to be completed until 2033, 2035, way after this whole project was to be completed. And with the $15.7 billion already invested in a project that has given you bridges here to my left and to my right, bridges to nowhere, right? But this project, if completed, 400 miles from LA to San Francisco, at best, it'll cost $106 billion. Now, most people will say that is a rosy estimate. There's no way it's going to be completed for $106 billion, which, just to do some simple math, that's 3 times.
Meanwhile, in China, since the Beijing-Tianjin line opened in 2008, China has built over 40,000 kilometers of high-speed rail, enough to circle the Earth at the equator, and then some. And the kicker? China's average construction cost is only 1/5 of California's high-speed rail project. It's like China is riding a rocket while the US is still on a bicycle. From the frozen highlands of the north to sun-drenched tropical shores, China's vast high-speed rail network keeps racing forward day in and day out. Now let's talk bridges. Sure, the Golden Gate Bridge is iconic, but today, 42% of US bridges are past their intended service life, causing an estimated $110 billion in economic losses every year due to aging and deterioration. In contrast, China is home to 8 of the 10 longest sea-crossing bridges in the world. And the construction efficiency? Absolutely staggering. In the US, building a standard bridge can take 7 to 10 years. But in China, advanced pivot technology has made it possible for a 16,300-ton bridge to rotate 180 degrees and connect in just 90 minutes. In 2019, the Pingshan Bridge in Hebei completed its pivot in only 85 minutes, a new world record. One American viewer even joked, "Do people in China have more hours in a day than we do?" So where does this massive gap come from? It boils down to fundamentally different approaches to infrastructure. In the US, projects often get stuck in endless rounds of approvals, local opposition, and political tug-of-war over funding. But in China, centralized planning and powerful execution enable the country to rally national resources for major challenges. Just look at the Hong Kong-Zhuhai-Macau bridge. More than 1,400 companies and tens of thousands of engineers work together on a single goal. That kind of nationwide coordination is nearly impossible to replicate in the US. And yet, in the face of what many consider a modern engineering miracle, some voices online from the US have raised doubts. With China's current level of industrial development, can this bridge really hold up? I bet it'll need a full overhaul in just a few years. It can't compare to Brooklyn Bridge, USA. This is just a showpiece, no real use. Just trying to flex on the world stage. A waste of money, purely symbolic, with no real benefit to the region. But these dismissive comments reveal less about the bridge and far more about their own comprehension limits. They conveniently ignore the 1,000-plus patented technologies developed during the construction. They overlook the 6.7-kilometer undersea immersed tunnel, built with a precision tolerance of less than 5 millimeters. And they're unaware of the bridge's advanced design, with multi-layered anti-corrosion systems, seismic resilience, and the ability to withstand Category 16 typhoons, magnitude 8 earthquakes, and even a 300,000-ton ship collision. When Chinese engineers declared a 120-year design lifespan, it wasn't a marketing slogan. It was backed by hard data, rigorous testing, and world-class engineering. These unfounded criticisms aren't about the bridge. They're about the growing unease of watching China's engineering capabilities rise, with a speed and confidence the world didn't expect.
Oh God, please, no! No!
Imagine this. Beneath the roaring waves of the Lingdingyang Strait, 33 massive immersed tunnel segments, each as tall as an 8-story building and weighing 80,000 tons, had to be aligned and joined together with Lego-like precision. The margin of error? No more than 5 centimeters. The difficulty? Comparable to threading a needle through a moving aircraft carrier during a hurricane. This was the hell-level challenge Chinese engineers faced while building the Hong Kong-Zhuhai-Macau bridge. John Smith, a member of the American Society of Civil Engineers, once said, "Achieving millimeter-level precision in deep-sea immersed tube joints, we used to think that was impossible in the real world." Faced with such skepticism, even ridicule from overseas experts, Chinese engineers responded with quiet determination. Yes, the difficulty is unprecedented. Millimeter-level tolerance in these conditions is an enormous challenge, but that's exactly why we must do it. This is our responsibility as Chinese engineers. We will not be intimidated by mockery or doubt, and no technological blockade can stop our progress. We will stay on site, research day and night, and even if we fail thousands of times, we will never give up. And they didn't. Through relentless effort, they invented a technique called composite foundation treatment, injecting special materials into the seabed to turn soft silt into rock-solid support, capable of holding tens of thousands of tons. During testing, engineers worked 72 hours non-stop, failed 137 times, until they finally achieved a 300% increase in load-bearing capacity. On May 2, 2017, during the connection of tunnel segments E29 and E30, a sudden tidal surge knocked them 3 centimeters off alignment. In that critical moment, China's self-developed dynamic hydraulic adjustment system kicked in, and within just 15 minutes performed a millimeter-level correction. This move didn't just save the project, it rewrote the rules of sea-crossing tunnel construction worldwide. Today, the 55-kilometer-long Hong Kong-Zhuhai-Macau bridge is not only the longest sea-crossing bridge in the world, it's a bold symbol of China's engineering prowess. Next, let's talk about water engineering. The Hoover Dam was once a global icon of industrial might, its power output unmatched for decades. But today, China's Baihatan Hydropower Station has taken center stage. Its network of underground chambers stretches over 217 kilometers. That's the length of 300 Empire State Buildings stacked end-to-end. The largest cavern is 438 meter long, 34 meter wide, and 88.7 meter tall, hence can easily accommodate 13 Boeing 737 aircrafts. And in terms of output, it generates 3 times the electricity of Hoover Dam. Even more astonishing, while America's Big Dig in Boston went 220% over budget and suffered decades of delays, China built Beijing Daxing International Airport, a massive starfish-shaped megastructure, in just 4 years. It handles 200,000 passengers a day and secured 60 international patents in the process. From cross-sea bridges to hydropower giants, from high-speed rail networks to clean energy megabases. Chinese engineers are pushing boundaries again and again, turning the impossible into reality. They are building, quite literally, the backbone of a nation's rise. These projects show that China doesn't just export infrastructure, it exports a complete development solution. Even the New York Times admitted, Chinese infrastructure is reshaping the global economic order. So how is China defining the next century of human progress? While the US is still fixing highways from the last century, China is already exploring the ultimate future of infrastructure. With each mega-project built, China continues to overcome world-class engineering challenges through innovative techniques and advanced construction methods, earning it the moniker infrastructure maniac. Moreover, China has undertaken major projects in numerous other countries, each emblematic of its development drive. Behind China's global leadership in infrastructure lies not only a leap in technology, but also the support of a mighty nation. For over a century, from the devastation at the founding of the People's Republic of China, it has been the successive struggles of generations of Chinese engineers that have painted the picture of today's prosperous China. And yet, this is not the end for China. In the future, the infrastructure maniac will continue to help more developing countries modernize, create new opportunities for development, and build a better, more livable world for all. Each bridge, every road, and every project connects cities and countrysides. The present and the future, China and the world. Chinese infrastructure has not only reshaped the face of China, but also exemplified the strength, spirit, and speed of the nation. And that is exactly why China is so often recognized around the world as the infrastructure maniac. This is not meant to be derogatory, but rather a tribute to China's remarkable achievements in infrastructure development. As one of the world's largest developing countries, China has continuously promoted its economic and social development through infrastructure construction. Chinese engineers seem like superheroes in the field of construction, dedicated to creating grand projects that meet the needs of the nation's growing population. As an old Chinese saying goes, to get rich, build roads first. Indeed, transportation is the cornerstone of economic development and a crucial guarantee. Prosperity can only come when people and goods can move smoothly. Engineering and technology are forces that reshape the world, accelerating the wheels of history and fueling the progress of human civilization. Today, as China rises to become the world's second-largest economy and the leading manufacturing powerhouse, it is also proving its extraordinary engineering capability, gaining global recognition as an infrastructure giant. A series of breathtaking mega-projects has showcased China's national strength and vitality to the world. Amid global economic shifts and China's new stage of development, these projects, defined by their massive scale, technical complexity, enormous investment, and long-term impact, span transportation, construction, water management, energy, and even defense. In just a decade, China has built and put into operation 45,000 kilometers of high-speed rail lines. By comparison, Japan and Europe took nearly 3 times as long to develop their own high-speed networks, and their scale is only a fraction of China's. Today, China's high-speed rail network alone exceeds the total of all other countries combined. Technologically, it has moved from importing to leading, pioneering the high-speed rail 4.0 era. The Three Gorges Dam is the largest and most complex hydropower project on Earth. The south-to-north water diversion project is the most ambitious interbasin water transfer in human history, and the land reclamation in the Nansha Islands has been hailed as a miracle of nature's craftsmanship. And among these mega projects, one is pushing the very limits of human engineering, the world's largest island-to-land connection project. From the sky, you're about to witness one of the boldest engineering feats on Earth, the Xiong'an Bridge, the world's largest island-to-mainland connection. Its 1,650-meter main span leaps across the sea in a single breath, holding the crown as China's longest-span bridge for 10 years straight. But this is just the beginning. Together with the Jintang, Taoyaomen, Xiang'an, and Chang'an bridges, a chain of mega-bridges stretches nearly 50 kilometers, binding once isolated islands into one seamless whole. 9 years later, the 8-kilometer Yushan Bridge rose to link Yushan Island with Daishan Island. 12 years after that, the 25-kilometer Zhoushan-Daishan Bridge connected Daishan Island to Zhoushan's main island. Together with the 32.5-kilometer Donghai Bridge, which links Shanghai to Xiaoyangshan Island, and the Liuheng Highway Bridge now under construction, A series of expressways have stretched across the sea, building new land right above the waves. The result? China gained the world's busiest cargo port, the second largest offshore green petrochemical base, and its very first major fishing ground. This is not just a bridge. It's a super connection that reshaped China's coastline and redefined what's possible in modern engineering. After conquering cross-sea bridges, China has set its sights on an even greater challenge: undersea tunnels. Here, you are about to see the world's longest undersea high-speed rail tunnel, the Jintang Undersea Tunnel, stretching 16.18 kilometers in total, with 11.21 kilometers of shield-driven section beneath the seabed. This tunnel is nothing short of a super engineering feat. Its cross-section measures a massive 14.5 meters in diameter, as tall as a 5-story building, large enough to accommodate dual high-speed rail tracks. The construction relies on the colossal shield machine, Ding'ai, with a cutter head nearly 15 meters across. Its steel blades work like the fangs of a giant beast, slicing through layers of rock and soil. Guided with pinpoint accuracy by China's Beidou satellite navigation system, it advances toward another shield machine, Yongzhou, coming from the opposite direction. Deep under the seabed, the two machines will finally meet with millimeter-level precision. So why is the Jintang Undersea Tunnel hailed as the world's #1? The key lies in one word: high speed. Its design speed reaches 250 kilometers per hour, far exceeding the Channel Tunnel between Britain and France in Japan's Seikan Tunnel. By high-speed rail standards, Jintang's length and scale are unmatched anywhere on Earth. But the greatest challenges are not just about being long. The tunnel runs 78 meters below sea level, where shield machines must withstand enormous water pressure. Along the route, they face 28 geological transitions, alternating between solid rock and soft soil. To overcome this, engineers made special modifications, adding water injection pipes on the cutter head to handle sticky clay, reinforcing the sealing systems to resist extreme pressure, and upgrading the drive system for long-distance stability. Construction follows a dual shield approach. Yongzhou advanced 4,940 meters from the Ningbo side. Ding'ai dug 6,270 meters from the Zhoushan side. Why the difference? Because the geology is uneven. Rock on one side, softer soil on the other, making symmetrical digging impossible. The final meeting point was deliberately chosen within a stable rock formation, the only way to guarantee a safe and accurate junction. And accuracy is everything. In an undersea tunnel, even the tiniest error in manual surveying multiplies over distance. One wrong calculation, and you could end up with two separate tunnels instead of one. To prevent disaster, engineers deployed 6 Beidou satellites linked to the shield machine's auto-navigation systems, correcting deviations in real time. In the end, the alignment error was kept within just 2 centimeters. Then came the final challenge: how to remove the machines. When the two titans meet underground, there is no exit ahead and no way back. The solution? A technique called shedding the shell. The shield machines are dismantled piece by piece and hauled out, while their massive steel casings remain in the tunnel, permanently reinforcing its structure. According to plan, the Jintang Undersea Tunnel will be fully bored through by the end of 2026 and open to traffic with the Yongzhou Railway in 2028. Once complete, passengers will be able to travel from Ningbo to Zhoushan in just 30 minutes by high-speed train, ending the island's long history of having no rail connection. And while officials may not say it openly, many already see the bigger picture. This tunnel is not just a passage to Zhoushan, it may well be the test bed for the Taiwan Strait Tunnel. If China ever attempts to build across the strait, this will have been the most critical rehearsal. So, just how advanced is China's technology for building underwater tunnels? To answer that, let's take the Hong Kong-Zhuhai-Macau bridge tunnel as an example. Here's the big question. The ocean is full of water. So how do you build a tunnel beneath the seabed? And how did Chinese engineers manage to construct a 6.7-kilometer underwater tunnel 40 meters below sea level? At first, engineers considered using tunnel boring machines. But since TBMS require extremely high stability, the tunnels they dug went much deeper than the design required. That meant they needed another solution. Their goal was to build a massive sea-crossing bridge that could connect Hong Kong, Zhuhai, and Macau, a project now hailed as one of the 7 wonders of the modern world. The final solution was immersed tube tunnel technology. In this method, trenches are dredged on the seabed. Prefabricated concrete tunnel sections, called immersion tubes, are then lowered into these trenches, aligned underwater, joined together, and finally backfilled with sand and gravel. Each tunnel section is 180 meters long, weighing 76,000 tons, about the same as an aircraft carrier. Each one contains 2 3-lane carriageways and 2 service tunnels. Chinese engineers had to lower and align these massive tubes one by one, but manufacturing a single 180-meter, 76,000-ton reinforced concrete unit in one piece was practically impossible. The solution? Engineers divided each tunnel section into 8 smaller parts, prefabricated them in a factory, and then joined them into a single 180-meter unit. In total, the project consumed 330,000 tons of steel and 2 million tons of concrete, enough to build 8 Burj Khalifa towers. On the uninhabited Niutu Island, over 3,000 workers built a massive factory in just 100 days. Its only task to produce the 33 immersion tubes required at a rate of 2 per month, each weighing 76,000 tons. After more than 1,400 days of construction, nearly all tunnel sections were in place. The final piece, E30, was carefully lowered into position. Slowly, steel cables lowered the giant section to the seabed, while engineers above monitored every detail in real time. After 26 hours of precise adjustment, E30 was finally seated in place. Divers then entered the seabed, carrying out millimeter-level measurements to ensure the alignment was perfect. Once confirmed, the last segment was sealed, and the world-shocking Hong Kong-Zhuhai-Macau bridge underwater tunnel was complete. This is not just about a tunnel. It's about speed, precision, and national ambition. A netizen compared China's rise to human learning. You get smarter from both success and failure. China is like a sponge, absorbing and improving technology. Many of these mega projects are not done for show, but to make things better. As one user put it bluntly, the US spends over $1.5 trillion on defense instead of modern infrastructure. Imagine what both countries could achieve if they worked together on infrastructure. One foreign commenter said, "These mega projects showcase China's engineering prowess and ambition, reshaping the country's landscape and connecting its vast population. But these projects come at a hefty price, often hidden from public view. The construction of these mega projects often involves massive land acquisition, deforestation, and the displacement of local communities. The environmental impact of these projects is significant, contributing to air and water pollution, habitat destruction, and climate change. Recent examples include the Three Gorges Dam, which displaced millions and altered the natural flow of the Yangtze River, and the Belt and Road Initiative, which has raised concerns about environmental sustainability in participating countries. While these projects promise economic growth, they often come at the expense of social equity and human rights. The construction of these projects has led to forced evictions, the suppression of dissent, and the exploitation of laborers. The lack of transparency and accountability surrounding these projects raises concerns about their social and ethical implications. Others see it in even grander terms. China is the first since ancient times, just sleepy for a while. Now it's returning to its rightful place. No one can stop it. Construction flows in the bloodstream of Chinese people. They have been building for thousands of years, and they're still building. The sky is the limit for China's achievements. From cross-sea bridges to underwater tunnels, from high-speed rail networks to megawater projects, China keeps redefining the limits of human engineering. These are not just structures of steel and concrete. They are symbols of ambition, vision, and determination. Of course, such projects spark debate worldwide. Some marvel at China's speed and precision, while others question the social and environmental costs. But one thing is undeniable. China has shown the world that the future is not something you wait for, it's something you build. So what do you think? Are China's mega projects a new chapter in human civilization or a massive gamble? Share your thoughts in the comments below. China has repeatedly pushed the limits of human engineering. These projects are not only transforming China, but reshaping the world. But this is just the beginning. In our next episode, we'll take you inside an even more audacious and strategic project, the Pinglu Canal. How will this canal of the century redefine the economy of Southwest China? And why did foreign viewers compare it to an alien base straight out of a science fiction movie? Join China as we decode this monumental project. It not only showcases the wonders of modern engineering, but also highlights the controversies and challenges it faces. Is this massive project the solution China has long been seeking? Or is it a colossal problem yet to be conquered? China's geography has played a crucial role in shaping its civilization and agricultural development. This vast country is home to diverse terrains, from the fertile plains along the Yangtze River to the arid expanses of the north. These geographical contrasts have not only influenced agricultural practices, but also shaped the historical development of communities across the nation. Let's begin with this map of China. Excluding Taiwan and the islands of the South China Sea, it marks 55 coastal cities in China. Among them, the vast majority have played vital roles in the country's economy, trade, transportation, and culture. Yet in the southwest corner of the map, the three coastal cities of Guangxi, Qinzhou, Beihai, and Fangchenggang have long remained a hidden corner under the halo of China's coast. Despite being born with natural deep-water harbors and holding the golden key of being China's only province-level region, directly connected to ASEAN by both land and sea, Guangxi has never received the status and attention it deserves. Even today, though the Beibu Gulf port has entered the top 10 Chinese ports by cargo throughput, when people mention Guangxi's coast, it is still seen merely as a destination of beautiful beaches and affordable vacations, rather than a hub of maritime ambition, prosperity, and strength. Guangxi's sea is modest, and its rivers seem even more reserved. Flowing through it is the Xiong'an River, Guangxi's most important water system and one of China's busiest inland waterways. Each year, over 200 million tons of cargo pass through the Xiong'an, but most of it eventually flows into the Pearl River Delta. Blocked by the 10,000 Great Mountains, this golden waterway nourishes a world-class bay area, yet it has little chance to directly benefit its own hinterland. Despite being coastal, Guangxi lacks a direct river-to-sea corridor. The world is clearly close, yet Guangxi has been forced to take the long way around. This is not only Guangxi's helplessness, but also a regret for the entire waterway system of southwest China. It is time to cut through the mountains with a canal to connect rivers to the sea. The Pinglu Canal is the first canal built since the founding of New China, and a century-defining project after the Grand Canal. The Pinglu Canal is a vital part of the new Western Land-Sea Corridor. It serves as a 100 million ton level water transport artery linking the Pearl River Zhejiang River Basin with the Beibu Gulf Port. Upstream, it connects with the Zhejiang shipping mainline, known as the Golden Waterway. To the west, it extends via the Yongjiang River directly to Nanning and the Zuo and Yu rivers, reaching into Yunnan. To the east, it flows through the Yujiang River straight to the Guangdong Hong Kong-Macau Greater Bay Area. To the north, it connects through the Qianzheng, Hongshui, or Liujiang rivers to Guizhou. To the south, it flows out into the Beibu Gulf. The Pinglu Canal has a total length of about 140 kilometers. It starts from the Pingtang River estuary of the Shijin Reservoir in Hangzhou, about 150 kilometers downstream of the Yongjiang River in Nanning. From there, it crosses the watershed between the Reshaping River and the Jiuzhou tributary of the Qinjiang River, runs through Luwu Town in Lingshan County, Qinzhou City, follows the mainstream of the Qinjiang River southward, and finally enters the waters of Qinzhou Port in the Beibu Gulf. Construction officially began in August 2022, with a planned duration of 52 months. The main structure is scheduled to be completed by the end of 2026. This new canal will become China's first major artificial canal in more than 1,400 years, since the famous Grand Canal itself. It will link the inland river system directly to the sea. This time, Guangxi's rivers will flow southward directly into the sea, rather than detouring through the more economically developed neighboring province of Guangdong. In fact, China has been considering digging such a new canal for decades. As you can see, the distance from Nanning to the Beibu Gulf is very short, just over 100 kilometers. The new canal will shorten the travel distance by 560 kilometers, which translates into about 10 days saved in transportation time. However, the Pinglu Canal comes at a hefty cost, with investment exceeding $10 billion. Is it truly worth it? The answer is certainly yes. Water transport is cheaper than road or rail. In addition, China has adopted a very conservative approach to forecasting returns, assuming that the investment will break even in 30 years. Yet the canal itself can last at least a century with minimal maintenance costs. To fully understand the economic benefits, one must also consider the additional 800 kilometers saved if cargo from Guangxi is destined for ASEAN countries. The canal will directly connect inland rivers to maritime trade with ASEAN nations, offering massive potential. Moreover, China already has methods in place to accelerate upstream and downstream cargo transport. The Pinglu Canal is designed with 3 locks, capable of accommodating ships of up to 5,000 tons. These locks will feature smart traffic guidance through data sharing. In China, only some sections of the Yangtze River can handle such large vessels, so the designers of the Pinglu Canal have clearly anticipated and planned for heavy shipping traffic in the future. Over the past decade, trade between Guangxi and ASEAN has accounted for nearly half of Guangxi's total trade, with its value almost tripling and its annual growth rate far exceeding the national average. All infrastructure construction is closely tied to market expectations. The Pinglu Canal will promote supply chain connections across industries such as automobiles and petrochemicals. Not only Guangxi, but also provinces in central and western China will benefit from it. As China accelerates the construction of river transport infrastructure, projects like the Pinglu Canal will usher in the next stage of economic growth and social empowerment. At first glance, it might seem like just a massive construction site, bulldozers, cranes, endless concrete. But in reality, what you are witnessing is China building its first major canal in over a millennium. And it's not just anywhere. It cuts through the most rugged terrain of southern China. You may have already marveled at China's construction speed, bridges spanning entire gorges, railways piercing mountains. But this time, they are doing something different. This is the Pinglu Canal, one of the most ambitious infrastructure projects in China in recent years. The Pinglu Canal stretches 134.2 kilometers, starting at the Pingtang River estuary of the Shijin Reservoir in Hangzhou and ending at the Qinjiang River flowing into the Beibu Gulf. This final connection to the sea is the key to the canal's significance. It transforms Guangxi's inland hinterland into a potential export hub. China has a long history of constructing artificial canals. The most famous is the Grand Canal, which stretches over 1,700 kilometers and has supported the nation's economic operations for centuries. From a bird's-eye view, we can easily spot the unique characteristics of the Grand Canal. On the plains of eastern China, it is the only north-south channel among all the east-flowing rivers. It not only links up the 5 major river systems, namely Hat River, Yellow River, Huai River, Yangtze River, and Shantung River, but also connects dozens of cities along the way, including Beijing, Tianjin, Jining, Yangzhou, and Hangzhou, all by itself, and it has been flowing for the last 2,500 years or so. It transported grain from the fertile southern regions to the political centers in the north and unified the national transport system during the Sui and Tang dynasties. However, after that golden age of water transport, China gradually shifted its focus to highways, railways, and aviation, especially after the 20th century. Water transport took a back seat. For over 1,000 years, China did not build any new large-scale artificial canals. So why revive this idea now? The reason is that China's economic landscape has changed. While the eastern coastal provinces remain manufacturing powerhouses, the central and western provinces, such as Guizhou, Yunnan, and Sichuan, are rapidly developing. These regions are far from the sea, and transporting factory goods to ports like Shanghai or Shenzhen takes both time and money. The canal offers a more efficient alternative, cheaper than rail, more energy-saving than trucks, and capable of transporting large volumes of cargo. This is the significance of the Pinglu Canal, not just reviving an ancient tradition, but solving modern logistics challenges. Just as the Grand Canal once transformed internal trade in ancient China, this canal will connect China's new regions to global markets. But this project is more than just pouring concrete. It involves logistics, strategy, economics, and possibly even political considerations. Theoretically, digging a 134-kilometer canal through hills and rivers might seem excessive, especially in a country with some of the world's busiest highways and advanced high-speed rail. But this is not about showing off. It's about solving a very real logistics problem. Many areas in western and southwestern China, such as Chongqing, Guizhou, and Sichuan, are industrially dense, with factories, coal mines, steel plants, and cement factories. But they share a common problem. They are landlocked, far from the sea. Transporting goods from these regions to eastern coastal ports like Shanghai or Shenzhen usually requires over 700 to 1,000 kilometers of travel, which is slow, costly, and heavily reliant on already overburdened railways and highways. The Pinglu Canal changes all of this. It provides these inland provinces with a direct waterway to the Beibu Gulf, which is crucial for companies shipping bulk goods. Even small transportation savings could determine profits or losses. This is not only a logistical improvement, but also part of a larger strategic plan. The canal plays a key role in China's new international land-sea trade corridor, linking railways, highways, and waterways, especially connecting underdeveloped Western regions directly to Southeast Asia and global markets. Construction officially began in August 2023, with a total budget of approximately $10 billion, and completion is expected in 2026. Once operational, ships will be able to transport goods between inland factories and international ports without using any highways or railways. The canal is designed to accommodate vessels up to 5,000 tons, primarily for bulk cargo. At full capacity, it is expected to transport over 95 million tons of cargo annually, roughly twice the early shipping volume of the Panama Canal. However, building a giant canal from scratch is no easy task, especially in uneven terrain. The Pinglu Canal must traverse mountains, hills, rivers, and villages, requiring road diversions, resident relocations, and terrain reshaping. The scale of work is enormous, with extremely precise requirements. Elevation differences exist along various parts of the canal, which is why 3 large locks, essentially water staircases, have been designed. The largest, the Tantang Lock, will be the largest water-saving lock ever built, allowing large vessels to navigate steep slopes while minimizing water consumption. This is particularly crucial in regions where seasonal droughts may cause water shortages. Along the canal, there are more than 90 bridges and over 40 kilometers of excavation zones, including several deep rock cuts. In some areas, up to 13 million cubic meters of earth must be removed, equivalent to more than 5,000 Olympic-sized swimming pools. Unlike older canals, this canal is built to modern standards: reinforced embankments, automated water control systems, and integration with intelligent logistics platforms. Thousands of workers and dozens of heavy machines, excavators, dredgers, and concrete pumps operate around the clock. Coordinating construction along such a long and narrow corridor is itself an engineering challenge. Once completed, the canal will function more like a highway than a traditional waterway, efficiently handling high-volume traffic with low maintenance costs. When people think of canals that transform cargo flows, they usually think of the Panama Canal and the Suez Canal, which connect oceans. The Pinglu Canal, however, is an inland canal linking rivers to a gulf, so it does not compete with Panama or Suez in global shipping. But that is not the point. Panama and Suez are shortcuts for international shipping, while the Pinglu Canal focuses on domestic efficiency. Despite its lesser fame, it is strategically just as important for China. At full capacity, the Pinglu Canal can handle over 95 million tons of cargo annually. This is not just an impressive number, it represents a major shift in how goods flow in southern China. Previously, cargo from inland factories to coastal ports had to travel 700 to 1,000 kilometers by truck or train, time-consuming and costly. This is especially significant for heavy materials like coal, cement, grain, or steel. The canal allows goods to float directly to the coast, cheaper, faster, and with lower emissions. Some routes are expected to shorten travel distances by up to 560 kilometers, saving about a day of transport time. This is a major benefit for China's inland provinces. Cities like Luzhou and Nanning, previously far from main shipping routes, now have the opportunity to become regional trade hubs. Industrial parks, logistics centers, and export zones are already being planned along the canal. The ports of the Beibu Gulf, especially Qinzhou, Fengchenggang, and Beihai, were previously considered second-tier ports, but with the continuous influx of inland cargo via the canal, they are becoming key players in China's overall trade strategy. Nationwide, the canal gives China greater control over internal logistics. No longer entirely dependent on a few eastern megacities, the country now has new routes to transport goods to Southeast Asia and beyond. In a time when global supply chains are under constant pressure, this flexibility is extremely important. The Pinglu Canal also strengthens China's trade links with Vietnam, Thailand, and Malaysia, creating a southern trade route that bypasses Taiwan or some sensitive South China Sea passages. In short, it is not just infrastructure, it is a strategic lever. Of course, large-scale construction projects always involve trade-offs. Excavating 134 kilometers of land inevitably affects local residents and the environment. Thousands of residents along the route have been relocated and many villages cleared. The government has provided compensation plans, but not everyone is satisfied. For older residents, losing ancestral land or being forced to leave long-established communities is not just about money, it concerns identity, history, and emotional attachment to the land. Environmentally, the canal passes through wetlands, farmland, forests, and biodiversity areas, placing pressure on local ecosystems, including fish, migratory birds, and groundwater resources. To mitigate this, the government and engineering teams have implemented multiple protective measures: ecological corridors, water-saving locks, real-time monitoring systems, sediment interception, and drainage facilities to prevent erosion and sediment damage to the rivers. Experts point out that these measures require long-term supervision and maintenance, especially during extreme weather, such as floods or droughts. The canal draws water from the Yujiang Reservoir in Hangzhou, which could affect agriculture and residential water use during dry seasons. Engineers state that this has been accounted for with reservoirs and water diversion systems, but uncertainties remain under climate change. Additionally, although water transport is generally more environmentally friendly than road transport, increased shipping brings risks of higher emissions, noise, fuel spills, or cargo leakage, particularly in previously quiet rural areas. Once fully operational, the canal will not only transport goods but could fundamentally transform how southern and western China participate in global trade. Local governments anticipate the canal transporting millions of tons of cargo annually, and as industrial zones, export hubs, and manufacturing parks develop along the route, this number could increase even further. However, such ambitious plans also carry risks. One major concern is underutilization. If companies do not adjust their logistics to fully leverage the canal, it could, like other large projects, remain partially unused after completion. Long-term maintenance is also a challenge. Locks, bridges, and automated systems require ongoing upkeep, especially during dry seasons when water levels and sediment accumulation need monitoring. Environmental management is another test. Despite official promises of real-time monitoring, responding to climate change and water resource pressures will require continuous investment and transparency. There is also a balancing issue. Can the canal provide economic opportunities without causing permanent damage to the environment and vulnerable communities? This is a matter that local governments must carefully manage over the long term. Undeniably, China is doing something that no other country in the world has attempted, building a high-tech inland canal system at record speed while addressing economic and strategic concerns. The Pinglu Canal may not make headlines like the Suez or Panama Canals, but it is equally important for China. This is a $10 billion infrastructure bet designed to activate inland trade, reduce transportation costs, and give the country more control over its supply chains. Construction is progressing rapidly, and China is betting on its success. If this project succeeds, the canal could become a benchmark for other countries around the world to reconnect their inland regions and reduce reliance on trucks and railways. So what do you think? Should more countries build inland canals to ease traffic congestion and lower logistics costs? Or are the environmental, social, and financial risks simply too high? Share your thoughts in the comments below, and don't forget to hit the subscribe button to join our channel. Because China's infrastructure story doesn't stop at its own borders. In fact, some of its most ambitious engineering projects are now reshaping entire regions beyond China itself. Take this railway, for example. It's doing something no one expected. It's killing sea trade. What used to take 40 hours now takes less than 5. And it's reshaping the entire map of Southeast Asia, built by Chinese engineers. For decades, the rugged mountains of Laos were more than just a landscape. They were a geographic prison. With only 7 kilometers of dilapidated railway in the entire country, Laos was the only landlocked nation in Southeast Asia, isolated, forgotten, and economically suffocated. But today the prison walls are falling. A 1,035-kilometer artery of high-grade steel and concrete has pierced through the roof of Indochina, executing a radical shift from landlocked to land-linked. This is the China-Laos Railway, a $6 billion geopolitical gamble that is rewriting the rules of global trade. As we enter 2026, the numbers are staggering. Over 72.5 million tons of cargo have already pulsed through this corridor, carrying more than 3,800 categories of goods, from sophisticated electronics to fresh agricultural exports. While the sleek Lancang EMU trains race at 160 kilometers per hour, the stakes are even higher than the mountains they tunnel through. This project isn't just about shortening a trip from days to a mere 10 hours. It's about a small nation balancing on a thin rail between unprecedented prosperity and a massive sovereign debt, nearly half of its GDP. Is this the dawn of a new Asian era or a golden cage of infrastructure? Let's dive into the details. In the high-stakes world of global engineering, every project has its enemies, usually gravity, weather, or budget. But for the 1,035-kilometer China-Laos Railway, the first enemy was a ghost. Between 1964 and 1973, Laos became the most heavily bombed nation per capita in history, with over 2 million tons of ordnance dropped across its landscape. Before a single sleeper could be laid, teams had to clear an estimated 80 million unexploded submunitions, still lurking in the shadows of the jungle. Commander-in-Chief Li Bin describes the early days as an invisible war, where demoners and local militias had to lead the way on foot, inching forward through no man's land because the terrain was too dangerous for heavy machinery to enter. For engineering head Liu Xianli, the fear of a hidden bomb detonating under a tunnel-boring machine was a daily psychological burden that defined the first phase of construction. Once the ground was cleared, the real battle against the roof of Indochina began. This is a journey through 167 bridges and 75 massive tunnels in the Laos section alone, representing 62% of the entire route. The map reveals a staggering complexity. The 9.59-kilometer Friendship Tunnel, which literally stitches two nations together, with 7.17 kilometers on the Chinese side and 2.42 kilometers reaching into Laos. But the crown jewel of difficulty was the Anding Tunnel, a 17,476-meter monster that forced engineers to innovate in ways never seen in Chinese railway history. They weren't just digging, they were fighting high rock temperatures, toxic gases, and water inrush. The engineering drama reached its peak at the Mekong River. Crossing the mother of rivers required the construction of two super major bridges near Luang Prabang. The Luang Prabang Bridge, spanning 1,458 meters with 34 massive spans, was a masterpiece of precision, completed 7 months ahead of schedule despite the turbulent currents. Further north, the Ban Laden Bridge stands as a testament to height, with its tallest pier reaching 57.5 meters into the sky, the highest in the entire project. Yet the greatest challenge wasn't just the height or the depth, it was the living rock. In the Hawaii Fulai Tunnel, what the Chinese engineers faced was Class 5 soft rock, which deformed at a rate of 10 centimeters per day. Imagine the pressure. As fast as you dig, the mountain tries to swallow you back. Chinese engineers not only conquered this tunnel through the detour parallel guidance method, they also tamed it, transforming a geological nightmare into a 160 kilometers per hour steel corridor. To understand the scale of this project, we must look beyond the steel and stone. By the end of 2025, the China-Laos Railway has officially evolved into the Golden Corridor of Southeast Asia. The data is staggering. As of early 2026, this 1,035-kilometer artery has pulsed with over 76.8 million tons of cargo, and the numbers are climbing faster than the trains themselves. We are no longer talking about just rubber and fertilizer. Today, more than 3,800 categories of goods, from sophisticated Chinese photovoltaic modules to high-end electronics and fresh-tied durians, are flowing across this border. At the Moan Railway Port, what used to be a 40-hour customs nightmare has been slashed to a mere 2 to 5 hours, thanks to advanced digital clearance systems. For the first time in history, the cost of logistics in landlocked Laos has plummeted by 20% to 40%, while freight costs between Kunming and Thailand have dropped by nearly half. But the real geopolitical earthquake is happening in the surrounding capitals. Witnessing this efficiency, Thailand has stopped being a spectator. The Thai government has recently approved the second phase of its high-speed rail project, a $10 billion investment to link Bangkok directly to this corridor via Nong Khai. They are even racing to build a second Friendship Bridge across the Mekong, dedicated exclusively to rail, to eliminate the current bottleneck and sync their standard gauge tracks with the Chinese system. However, every miracle has its price. The $6 billion construction cost represents a massive financial weight for Laos, a nation whose debt to GDP ratio has ballooned beyond 100%. The ownership structure is a delicate 70-30 split between Chinese state-owned giants and the Lao National Railway, but the lion's share of the funding, about $3.5 billion, is a loan from the Export-Import Bank of China. Critics call it a debt trap, warning that Laos is balancing on a razor's edge. Yet China views it as high-quality development, a cornerstone of the 15th five-year plan that institutionalizes China's push for regional integration. This is not just a railway, it is a structural axis. It has integrated the Vientiane-Saisita development zone into a global supply chain, attracting industries in healthcare, new materials, and biopharmaceuticals that never thought of Laos as a destination. As the trains race toward 2030, the question remains, is Laos becoming a strategic hub that powers ASEAN, or is it becoming an economic satellite of the Dragon? One thing is certain, the map of Southeast Asia has been permanently altered, and there is no going back. To the average traveler, the Lancang EMU is just a sleek, lime green bullet train, but to an engineer, it is a masterclass in adaptation. These CR200J train sets, specifically the 5th generation introduced for the 2025 to 2026 season, were forced to solve a physics nightmare: how to maintain high-speed stability in a country that is essentially a humid, mountain-strewn greenhouse. Unlike the standard Fuxing models running between Beijing and Shanghai, the Lancang is built with a tropical defense architecture. Engineers from CRRC Pugen and Zhuzhou applied a specialized environmentally friendly paint technique that achieves a mirror-like surface gloss of greater than or equal to 95 GU. This isn't for aesthetics, it's a high-density clear coat 3 times thicker than the industry standard, designed to repel the corrosive effects of Laos' extreme ultraviolet rays and its relentless monsoon rains that can reach 3,000 millimeters annually. But the real magic happens at the entrance of a tunnel. Remember, this line has 75 tunnels in the Laos section alone. When a train enters a tunnel at 160 kilometers per hour, the air pressure spikes instantly, a phenomenon that can cause severe ear discomfort or even structural fatigue over time. The Lancang is equipped with an active pressure stabilization system. Within milliseconds of sensing a pressure change, automated protection devices seal the cabin's air valves, maintaining a constant internal atmosphere. This allows passengers to sip their Laotian coffee in total silence and comfort while the train pierces through the rock. 1,300 new seats were added to the fleet in early 2025 to meet the exploding demand. Look at the upholstery. It's not just fabric, it's a tapestry of the Dok Champa, the national flower of Laos, woven with Chinese precision. This train doesn't just transport people, it's a high-speed diplomatic mission that runs on 25,000 volts of electricity. While the steel rails provide the path, a digital nervous system provides the safety. This is Southeast Asia's first truly smart railway. Partnering with Huawei and China Railway Electrification Engineering Group, the project installed a full-coverage 5G network across the entire 508-kilometer Chinese section and the 422-kilometer Laos section. But this isn't for streaming movies. It's the backbone of the 4-1's management system. This AI-driven command center uses IoT sensors embedded in the track bed to monitor for the slightest vibration. In the treacherous Undersea province, where landslides are a seasonal reality, these sensors can detect falling debris and trigger an emergency stop signal to the driver's cab long before the train reaches the hazard. High-speed trains continue to run along the tracks, while sensors simultaneously record every aspect of their operation. Facing complex environments and ever-changing weather conditions, China's high-speed rail technology is constantly being tested for reliability. All of this data is precisely recorded. Today, Chinese engineers have never stopped developing new high-speed rail technologies, and in the foreseeable future, even more innovations will be applied to China's vast, independently developed high-speed rail system. At the Mohan land port, technology has killed the customs nightmare. Robotic scanners now check truck undersides in seconds, and shared digital lanes mean drivers stop only once instead of twice. Clearance times for cross-border cargo have plummeted from 40 hours to less than 5 hours, an efficiency leap of 800%. Simultaneously, the project had to answer a critical question: can a mega project be green? The answer lies in 3.07 million square meters of reclaimed vegetation. Chief engineer Huang Daiwen and his Blossom team rejected the idea of using imported seeds. Instead, they spent years working with local villagers in Vang Vieng and Luang Prabang to transplant native seedlings. This ensured that the railway didn't introduce invasive species into the primary forests. Furthermore, for the wild Asian elephants that call the Sichuan-Bana Laos border home, the railway is practically invisible. Engineers built specialized viaducts and 62 kilometers of safety fencing designed to guide elephants towards safe wildlife corridors. By the time we hit the 15th five-year plan in 2026, this beautiful China philosophy has turned the rail line into a continuous ecological promenade. where the carbon footprint of shipping a ton of goods has been reduced by 30% compared to road transport. In global logistics, even a small mismatch can break the entire system. A difference of just 43.5 centimeters means trains can't run across borders. China and Laos use the standard gauge, 1,435 millimeters, but the legacy tracks of Thailand, Malaysia, and Singapore use the meter gauge, 1,000 millimeters. Without a solution, Vientiane would have been a dead end. Enter the Thanaleng Dry Port, TDP, a $727 million logistics miracle that serves as the Lao logistics link. Opened officially in December 2021, this facility features a specialized rail transshipment yard. Imagine a massive ballet of steel. A freight train from Kunming arrives on one side, and within minutes, reach stackers and gantry cranes swap thousands of containers onto Thai trains waiting on the other side. This logistical bridge is why Laos's customs revenue from import taxes has trebled in just 3 years. The TDP is the vital organ that connects the Vientiane Seta development zone to the world. By early 2026, the port is handling over $7,000 containers per month, carrying everything from Russian fertilizer to European machinery. On January 3rd, 2026, we witnessed a historic breakthrough. The first shipment of frozen Thai shrimp from Songkhla traveled through Thanaleng to China in record time, slashing previous sea route transit times by 60%. This is the petiole effect. Just as a petiole connects a leaf to its branch, Thanaleng connects the inland veins of the Asian continent to the global maritime trade routes of the Beibu Gulf and beyond. As Thailand moves toward completing its $10 billion high-speed link to Nong Khai by 2028, this transshipment hub will become the busiest inland port in ASEAN, proving that geography is no longer a destiny, but an opportunity. The story of the China-Laos Railway is not an isolated event, it is the opening movement of a continental symphony. Under the roadmap of China's 15th five-year plan, this corridor is the definitive blueprint for high-quality development. We are seeing the birth of a new professional class in Laos. Look at Somse Lalyu, a 24-year-old who started with zero railway knowledge and now leads a team of 992 Lao railway professionals. He isn't just a driver, he is the face of a nation that has traded its isolation for a seat at the head of the regional economic table. By the end of 2025, the railway has handled over $66 million passenger trips, with $12 million of those on the Laos section alone. This human flow is rebuilding the Indo-China corridor into a zone of shared prosperity. As we look toward 2030, the momentum is unstoppable. Malaysia's East Coast Rail Link, ECRL, is pushing past 92% completion, and Thailand is accelerating its high-speed integration. The dream of a seamless journey from the skyscrapers of Beijing to the ports of Singapore is no longer a what-if. It is an engineering certainty. Yes, the shadow of $6 billion in debt remains a serious challenge for Laos sovereignty. But the pulse of the Golden Corridor is creating a new reality where landlocked countries are no longer victims of their borders. The dragon hasn't just arrived, it has built the foundation for a 3,000-kilometer artery that will define Asian trade for the next century. From the roof of Indochina to the tropical shores of the South China Sea, the map has been permanently electrified. The prison is gone. The link is eternal. The China-Laos Railway has successfully dismantled a geographic prison, proving that steel and ambition can redraw the map of Asia forever. It is the definitive blueprint for a connected continent. It proved that geography is no longer a limitation, but a variable that can be engineered. From a landlocked nation to the center of a new continental network, this is what happens when infrastructure becomes strategy. But here's the real question. If a single railway can reshape Southeast Asia, what happens when entire oceans are no longer barriers? Because right now, Chinese engineers are attempting something even more extreme. A 123-kilometer tunnel built beneath the sea, a project so ambitious it could redefine global trade once again. And if you want to understand the real forces reshaping our world, make sure to subscribe, because this is just the beginning. Look at a map of China, and you will see a geographic injustice that has haunted its leaders for millennia. There is a hidden boundary known as the Hu Line that divides the nation in two. To the east of this line lives 94% of China's population, fueled by the massive industrial engines of Beijing and Tianjin. Yet this region possesses only 20% of the country's total freshwater resources. While the south is frequently devastated by massive Yangtze floods, the north is being slowly devoured by the Gobi Desert, which expands by 3,600 square kilometers every single year. For decades, northern cities like Beijing have survived by overexploiting their groundwater. causing the very land beneath them to sink by several centimeters annually. This isn't just an environmental issue. It is a ticking geopolitical time bomb. If the north runs dry, the Chinese economy collapses. To prevent this catastrophe, Beijing has launched the South-North Water Transfer Project, a $62 billion war against nature itself. We are talking about thousands of kilometers of artificial canals, massive aqueducts, and deep earth tunnels designed to borrow the South's water to quench the North's thirst. This is the story of how China is literally replumbing the planet to ensure its survival as a global superpower. The idea of rearranging China's entire water system didn't start in a modern lab. It began with a single, bold sentence uttered in 1952. While standing on the banks of the Yellow River, Chairman Mao Zedong famously remarked, "The South has plenty of water, the North has little. It would be fine to borrow some if possible." This wasn't just a casual observation. It was a command that launched 50 years of intense scientific debate and grueling geological surveys. It wasn't until 2002, after decades of technical vetting, that the State Council finally greenlit the South to North Water Transfer Project. Since then, the project has evolved from a mid-century dream into a cornerstone of absolute national security. In 2020, Beijing took a massive step by consolidating the entire operation under a new, powerful, state-owned entity, the China South to North Water Diversion Group. This transition marked a strategic shift from simple construction to an era of high-tech, AI-driven management. For the leadership in Beijing, water is no longer just a resource. It is the lifeblood of social stability and industrial survival. By investing over $62 billion in the initial stages alone, China is proving that its political future depends on its ability to correct the mistakes of geography. This is Mao's vision, powered by 21st century ambition, ensuring the thirsty North never stops growing. Moving from history to hardware, we drop our third marker on the eastern route, a 1,156-kilometer technical feat that repurposes the ancient Grand Canal. Unlike the other paths, the eastern route must overcome a massive geographical challenge, pumping water uphill. To achieve this, China has constructed the world's largest pumping station cluster, consisting of 23 high-capacity stations divided into 15 stages. Under the leadership of Chairman Zhang Shuguang, the project has integrated sophisticated hydraulic turbines that lift nearly 15 billion cubic meters of water annually from the Yangtze River Basin toward the industrial hubs of Shandong and Tianjin. The energy requirement alone is massive, yet the system achieves an efficiency rate of over 80% through automated flow control algorithms. Currently, this route provides a stable water supply to over 100 million people and sustains agricultural production across 200,000 square kilometers of previously parched land. Strategically, this route functions as a massive industrial artery, reducing the North's dependence on unstable rain patterns and deep well extraction by 30%. By 2026, the second phase of expansion aims to increase the delivery capacity to 30 billion cubic meters, cementing the eastern route as a permanent, high-volume insurance policy for China's coastal economy and food security. While the eastern route relies on the raw power of massive pumps, the true engineering soul of this project lies further inland. Here, the central route, the absolute backbone of China's water strategy, achieves a nearly impossible feat: a constant flow across 1,276 kilometers without a single mechanical pump. This is a masterpiece of hydraulic physics, relying entirely on gravity to deliver water from the Danjiangkou Reservoir straight to the heart of Beijing. To make this downward flow possible, engineers performed high-stakes surgery on the landscape, raising the existing Danjiangkou Dam by 15 meters to hit a staggering storage capacity of over 29 billion cubic meters. This technical triumph came with a heavy human price: the strategic relocation of 330,000 people, a movement handled with the precision of a national military operation. Under the watchful eye of Chairman Zhang Shuguang, the water travels through the 12-kilometer Shahe Aqueduct and dives deep beneath the Yellow River through massive concrete tunnels. By 2026, this $62 billion network is being reinforced by the Yinjiangbuan Tunnel, a deep earth artery designed to replenish the Han River from the Three Gorges. Today, this route provides 70% of Beijing's freshwater, delivering over 9 billion cubic meters annually. And the starting point of all this comes from the Danjiangkou Reservoir in Hubei, A stream of clear water sets off from here, beginning a long northward journey across the map of China. With a total length of over 1,400 kilometers, this is not just a canal, but a lifeline that runs from south to north. It passes through 4 provinces and municipalities, and through hundreds of sluice gates, provides stable water supply to more than 20 large and medium-sized cities, as well as over 200 counties. But what is more complex is the system engineering behind it. This water artery does not just transport water, it must also provide ecological replenishment for dozens of rivers, maintaining the balance of the entire regional water cycle. The problem is, once any single gate loses coordination, the entire canal will fall into paralysis. And what is even more severe is nature itself. This route spans 8 latitudes and 2 temperature zones. While the southern sections may still be under blazing sun, the northern sections may already begin to freeze. Ice can block the flow of water and even directly interrupt the entire water transfer system. So, is it possible to predict in advance water levels, flow velocity, water temperature, and even the freezing risk of each section of the canal? The answer is yes. But the premise is, there must be a digital replica of the real world. All the regulating gates, drainage gates, diversion outlets along the canal, as well as more than 100,000 sensors and over 10,000 monitoring devices, are all connected into one unified system. This turns the 1,000-kilometer artificial river into not just flowing water, but a super system that is calculated in real time and precisely controlled. It isn't just a canal, it is a sovereign lifeline, proving China can reshape its topography to sustain its political heart. While the central route is a triumph of surface physics, its long-term survival depends on a hidden monster buried 1,000 meters beneath the Earth's crust. This is the Yinjiangbohan Tunnel, the world's longest and deepest water diversion tunnel, currently the most sophisticated subterranean project in China's history. Spanning 194 kilometers, this massive artery is designed to link the Three Gorges Dam on the Yangtze directly to the Han River, effectively recharging the entire central route. Under the command of Chairman Zhang Shuguang, engineers are currently engaged in a brutal technological war against the Earth. Using custom-built tunnel boring machines the size of buildings, they are carving through high-pressure tectonic zones where rock temperatures exceed 40 degrees Celsius. The scale of this $8 billion project is staggering. It aims to transport nearly 4 billion cubic meters of water annually to ensure the North's industrial heart never skips a beat during seasonal droughts. Strategically, moving this much water underground prevents evaporation and eliminates the risk of surface pollution. By 2030, this underworld highway will turn the Yangtze and Han rivers into a single synchronized engine of prosperity. It is a sovereign statement of deep earth mastery, proving that China doesn't just build across the landscape, it owns the space beneath it, securing its water future through absolute engineering dominance. While the tunnels of central China conquer the underworld, the final frontier of this hydraulic war reaches for the heavens. We are looking at the western route, the most ambitious, difficult, and geopolitically explosive phase of the entire project. This stage requires engineers to carve through the Qinghai-Tibet Plateau at altitudes ranging from 3,000 to 5,000 meters above sea level to connect the headwaters of the Yangtze and Yellow rivers. Under the long-term strategic vision led by Chairman Zhang Shuguang, this route aims to divert an incredible 17 billion cubic meters of water annually toward the parched western provinces. But the engineering is only half the story. Because these waters feed the great rivers of Southeast Asia and India, the project has triggered an international alarm. New Delhi watches with growing concern as Beijing prepares to build dams and tunnels on transboundary rivers like the Brahmaputra, effectively holding the water tap of Asia in its hands. The technical challenges are staggering. Constructing thousands of kilometers of channels in a high seismic zone where the Earth is literally still rising. By pushing into the Himalayas, China isn't just seeking to green its deserts, it is securing absolute hydrological dominance over the continent. This is the ultimate chess move in the great game of the 21st century, turning the roof of the world into a sovereign valve for a thirsty empire. Beyond pipes and canals, China's water project uses a digital nervous system, the AI brain. By 2026, Smart SNWTP will monitor the 3,000-kilometer network using 100,000 IoT sensors. Managed by Chairman Zhang Shuguang, this digital fortress relies on Beidou 3 satellites for millimeter-level precision. AI algorithms process billions of data points daily to predict floods and adjust flows instantly. This ensures absolute security. Sensors detect pollutants and trigger automated gates to protect northern reservoirs. By integrating 5G and big data, Beijing has transformed the world's largest plumbing project into a sophisticated technological asset, ensuring the North's industrial engine never runs dry. Every engineering triumph has a shadow. This $62 billion project has forced 600 natural rivers to vanish or dry up. As the Yangtze's flow dropped by 36% upon the central route's opening, a new crisis emerged: saltwater intrusion. In cities like Shanghai, the Yellow Sea now pushes backward into freshwater supplies. While Chairman Zhang Shuguang oversees massive filtration, industrial waste from cities like Xiong'an remains a persistent threat to reservoir quality. Beijing is effectively trading the ecological health of the South for the survival of the North, proving that even a superpower cannot defy nature without paying a devastating environmental price. 2026 is the year China proves its engineering dominance is about strategic speed and long-term vision. From the Himalayas to the digital streets of Xiong'an, the map is being redrawn. But while these projects are public, one massive operation remains in the shadows. From the high-altitude permafrost of the Tibetan Plateau to the artificial islands of the South China Sea, China is about to activate a network of megaprojects that will redefine regional power. We aren't just talking about big buildings. We are talking about the world's fastest commercial trains, dams that rival mountains, and the dawn of modular nuclear energy. But it's actually not that easy to find reliable information about their most recent projects, at least not in Western media. In this video, we go under the concrete. We analyze the 10 most extreme projects completing in 2026, breaking down the billions invested, the technical breakthroughs, and the geopolitical chess moves that make these projects much more than just infrastructure. This is China's 2026 revolution. Imagine traveling from Beijing to Shanghai, a distance nearly equal to London to Rome, in just about 2 hours. By 2026, the CR450 turns this impossible dream into a terrifyingly fast reality. We aren't just talking about standard high-speed rail, we are talking about hitting 450 kilometers per hour. To put that in perspective, this train moves faster than most civilian helicopters can fly. Engineering this required a radical material revolution. The research teams at the China Academy of Railway Sciences had to solve the tunnel piston effect, a massive buildup of air pressure that could literally shatter windows when a train enters a tunnel at such velocities. Their solution was an aerodynamic nose design inspired by birds of prey and a body crafted from lightweight carbon fiber composites. This reduces the total weight by 12% while cutting energy consumption by 10% compared to the older CR400 models. Geopolitically, the CR450 is China's declaration that the era of Western or Japanese rail dominance is officially over. By owning the intellectual property for the high-torque permanent magnet motors and the 5G integrated signaling systems, China is preparing to export this entire technological stack across the Belt and Road Initiative. The CR450 is the 2026 milestone that secures China's crown as the world's undisputed high-speed rail king. Next, we move to the roof of the world for a project that redefined the term impossible, the Sichuan-Tibet Railway. Stretching 1,600 kilometers through the most treacherous terrain on Earth, this is often hailed as the Heavenly Road. By 2026, the hardest sections, the high-altitude tunnels, are finally nearing completion. This is a brutal engineering war against permafrost, thin oxygen, and extreme seismic activity caused by the Indo-Eurasian plate collision. To put the scale in perspective, the railway features 72 massive tunnels and 93 bridges, crossing 14 major rivers. Chief engineer Lin Shijin had to design custom oxygen-enriched boring machines just to keep his workers alive in the thin mountain air. Why build it? The numbers tell the story. It slashes travel time from 48 hours to just 12. But the real motive is purely geopolitical. For China, this is a $47 billion strategic anchor, securing the Tibetan frontier and integrating it forever into the Chinese national economy. It acts as a permanent high-speed umbilical cord that transforms a remote, isolated border into a vital economic artery. While Western projects often stall at the planning stage for decades, China is literally moving mountains to ensure its sovereignty is etched in steel across the Himalayas. Himalayas. This isn't just a train, it's a geopolitical masterpiece. Dropping our third marker on the map, we head to the industrial heart of the South, the Pearl River Delta. Here, the Shenzhen-Zhongshan link is not just a bridge. It is a $6.7 billion symphony of steel and concrete designed to conquer the sea. Spanning 24 kilometers, this project features a record-breaking undersea tunnel consisting of 32 massive steel shell tubes, each as large as a commercial aircraft. Chief engineer Song Shen-yu faced a technical nightmare, docking these structures 80 meters below the surface with millimeter precision amidst treacherous maritime currents. By 2026, the full impact of this project becomes clear as it slashes travel time across the bay from 2 hours to just 30 minutes. Geopolitically, this is the final piece of the Greater Bay Area puzzle, an economic powerhouse designed to rival Silicon Valley. By seamlessly integrating Shenzhen's tech core with Zhongshan's manufacturing base, China is creating a mega region with a combined GDP that surpasses many developed nations. The link is an engineering statement proving that China can build a massive undersea artery while maintaining a high-speed 8-lane highway. It represents the absolute pinnacle of maritime construction, a record-breaking gateway that ensures China's economic engine never stops accelerating, cementing its status as the world's logistics superpower. Heading back to the rugged canyons of Sichuan province, we encounter a titan of energy, the Shuangjiangkou Hydropower Station. By 2026, this massive structure will reach its final height of 315 meters, officially becoming the tallest dam on the planet. To visualize that, it stands taller than the Eiffel Tower, holding back a staggering 3 billion cubic meters of water. The engineering challenge was immense. Chief engineer Lu Jun and his team had to construct a rock-filled dam capable of withstanding massive seismic pressure in a high earthquake zone. This required the precise layering of over 44 million cubic meters of material managed by a fleet of autonomous AI-guided trucks and rollers. Why is this critical now? Because Sichuan, China's industrial powerhouse, faces increasingly severe droughts. This $5.6 billion project acts as a strategic water battery, regulating the Dadu River and providing over 7 billion kilowatt hours of clean electricity annually. Geopolitically, it is a cornerstone of China's west-to-east power transmission strategy. While other nations debate energy transitions for decades, China is literally carving out the future of renewable energy in solid rock. It is a massive statement of water and energy sovereignty that ensures China's industrial wheels keep turning regardless of the weather. This dam isn't just infrastructure, it is China's insurance policy for a carbon-neutral future. Dropping our next marker on the eastern coastline, we arrive at the Xiong'an International Airport, a project where China is literally creating land from the sea. By 2026, the first phase of this $10 billion mega project will be ready to handle 45 million passengers annually. The engineering drama here lies beneath the waves. To create 25 square kilometers of territory, engineers had to reclaim over 1,000 hectares from the ocean, stabilizing a treacherous, soft seabed that threatened to swallow the foundations. Chief designer Li Tai utilized advanced vacuum preloading techniques to transform liquid sea mud into solid, buildable ground. The terminal itself is an architectural masterpiece designed to resemble a great swallow, featuring a massive curved roof that blends traditional Fujian aesthetics with futuristic, sustainable tech. Why build it on an island? Because Xiamen is a strategic pivot for the 21st century maritime Silk Road. Geopolitically, this hub is China's bid to dominate air traffic in the Taiwan Strait, while providing a high-tech alternative to regional hubs like Hong Kong or Singapore. By 2026, Xiong'an will be the primary engine for the Southeast International Shipping Center, proving that when China runs out of land to build, it simply engineers new territory from the waves. This isn't just an airport, it's a sovereign statement of maritime expansion. Our sixth marker lands in the subtropical southwest, where China is digging its first major canal in over 1,000 years, the Pinglu Canal. This 130-kilometer waterway is the crown jewel of the new Western Land Sea Corridor, designed to connect the city of Nanning directly to the Gulf of Tonkin. The engineering scale is monumental. By 2026, excavation teams will have moved over 340 million cubic meters of earth. That is roughly 3 times the volume of the original Suez Canal's excavation per kilometer. Chief engineer Cheng Jitao and his massive fleet of dredging machines are literally carving a highway for 5,000-ton ships through the heart of Guangxi province. Why does this matter? Currently, goods from inland China must travel through the congested Pearl River Delta, adding hundreds of kilometers to the journey. The Pinglu Canal slashes this distance by over 500 kilometers, saving billions in logistics costs annually. Geopolitically, this is China's direct bridge to ASEAN markets, bypassing traditional bottlenecks and securing its trade dominance in Southeast Asia. This $10.3 billion canal isn't just about moving cargo. It's about shifting the economic center of gravity of Western China toward the ocean. By 2026, this subtropical Panama Canal will be a reality, cementing China's status as a global logistics architect. Our seventh marker takes us to the tropical island of Hainan, where China is pioneering the future of global energy, Linglong 1. By 2026, this compact powerhouse will officially begin commercial operation, marking it as the world's first small modular reactor, or SMR, built for land-based commercial use. While traditional nuclear plants are massive, multi-decade projects, Linglong 1 is a masterclass in modularity. Chief engineer Song Dan-rong and his team designed the reactor so its core components could be manufactured in a controlled factory environment and simply shipped to the site for assembly, much like a high-tech Lego set. This revolutionary approach slashes construction time to just 5 years and significantly lowers initial costs. With a power output of 125 megawatts, this single unit can generate 1 billion kilowatt hours of electricity annually, enough to power over 500,000 homes while cutting nearly 1 million tons of carbon emissions. Geopolitically, this isn't just about Hainan's energy, it's about export dominance. China is positioning itself as the primary supplier of SMR technology for developing nations that cannot afford traditional gigawatt-scale plants. Linglong 1 is Beijing's strategic tool to lead the global nuclear renaissance, offering a scalable, safe, and carbon-neutral energy solution to the world. Dropping our eighth marker into the misty mountains of Guizhou province, we find ourselves staring into the abyss at the Huajiang Canyon Bridge. By 2026, this structure will officially claim the title of the highest bridge in the world, suspended at a dizzying 625 meters above the river surface. To put that in perspective, you could stack 2 Eiffel Towers beneath its deck and still have room to spare. Engineering a suspension bridge at this altitude is a nightmare of aerodynamics and structural precision. Chief engineer Liu Hao and his team utilized ultra-high-strength steel cables and massive anchorage systems drilled deep into the limestone cliffs to withstand the unpredictable mountain winds. This bridge is a vital link in the G60 expressway, slashing the travel time across the canyon from over 70 minutes of dangerous winding roads to just 1 single minute of smooth transit. Geopolitically, this project cements Guizhou's status as the global museum of bridges and proves China's absolute mastery over vertical terrain. While other nations struggle to maintain aging infrastructure, China is literally weaving a web of steel across the heavens to integrate its mountainous hinterland into the national economic engine. The Huajiang Canyon Bridge isn't just a road, it's a monument to China's engineering audacity. Moving north to the outskirts of Beijing, our ninth marker lands on the most ambitious urban experiment in human history, the Xiong'an New Area. Often called the city of the future, Xiong'an is China's $400 billion answer to the chaos of modern megacities. By 2026, the world will witness the full realization of a digital twin city, where every physical building has a virtual counterpart in the cloud for real-time AI management. But the real engineering genius is hidden beneath your feet. Chief planner Zhao Peng and his team have designed a city where logistics, utilities, and even waste management are moved entirely underground, leaving the surface for parks and pedestrians. This is the world's first sponge city built from scratch, engineered to absorb and reuse nearly every drop of rainwater. The numbers define its efficiency, a 15-minute life circle where every resident is within a short walk of all essential services, powered by a dense network of over 3,000 5G base stations. Geopolitically, Xiong'an is Beijing's blueprint for the 21st century urban model, a direct challenge to the aging, congested cities of the West. It is a strategic relief valve for the capital, proving that China can not only build massive infrastructure, but can invent an entirely new way of living. By 2026, Xiong'an will stand as a sovereign statement of technological and social harmony. For our final marker, we travel to the vast, windswept plains of the Gobi Desert, where China is constructing the world's largest green energy machine. By 2026, these massive wind and solar bases will reach a critical milestone, contributing to a staggering goal of 450 gigawatts of renewable capacity. To visualize this project alone will eventually generate more electricity than the entire power grids of most European nations combined. The engineering challenge is a continuous battle against the elements. Chief Engineer Li Guoping leads a mission to deploy millions of solar panels and thousands of high-altitude turbines in one of the harshest environments on Earth, where sandstorms and extreme temperatures are the norm. To solve the problem of distance, China developed ultra-high voltage transmission lines, a revolutionary energy highway that transports electricity over 2,000 kilometers to the coastal megacities with almost zero loss. Geopolitically, the Gobi Project is China's ultimate shield for energy security. By harvesting the sun and the wind, China is systematically breaking its reliance on foreign oil and coal imports, effectively insulating its economy from global price shocks. This $40 billion annual investment isn't just a green initiative. It's a strategic masterstroke that cements China's status as the world's first renewable superpower. The Gobi Desert is no longer a wasteland. It is now the beating heart of the world's energy future. 2026 is the year China proves its engineering dominance isn't just about massive scale, it's about strategic speed and a vision that looks decades ahead. From the frozen peaks of Tibet to the digital streets of Xiong'an, the map of Asia is officially being redrawn in steel and silicon. But while these projects are public, there is one massive operation China is still keeping in the shadows. If you think these 10 projects are extreme, wait until you see the one they are building in secret right now. Imagine landing a massive jet in a place where the air is so thin, your lungs scream for oxygen and engines lose their breath. Welcome to the forbidden zone of the Tibetan Plateau. You are standing at 4,411 meters above sea level, nearly halfway to the cruising altitude of a commercial flight. At this altitude, the laws of physics are your enemy. The air pressure is 40% lower than at sea level, turning a routine landing into a high-stakes survival challenge. Most engineers said an international standard airport here was impossible. Why? Because thin air provides zero lift. To take off, a plane needs raw, unadulterated speed. But the challenge wasn't just flying, it was building. How do you pour concrete that freezes instantly in sub-zero winds? China didn't just build a terminal, they built a $250 million flying saucer that defies nature. They transformed a desolate rock into a strategic gateway, proving that if the geography doesn't suit your ambition, you simply rewrite the map. But what secrets lie beneath this silver dome? And how does it survive the brutal Himalayan winters? Let's dive into the technology of the airport that shouldn't exist. To understand the necessity of Daoxing Yading Airport, you have to look at the map of Western Sichuan. For centuries, this region was a forbidden zone, locked behind the impenetrable wall of the Hengduan Mountains. Before the airport, the journey from Chengdu, the nearest major provincial hub, to Daocheng was a grueling 800-kilometer test of human endurance. It wasn't a drive, it was an expedition. Travelers had to navigate narrow, winding roads carved into the sides of cliffs, facing unpredictable mudslides, heavy snowfall, and treacherous mountain passes that exceeded 5,000 meters in altitude. In good weather, the trip took a minimum of 2 full days. In bad weather, you could be stranded for a week. This isolation wasn't just a tourist inconvenience, it was a socio-economic barrier. For the local Tibetan communities in the Garzei Autonomous Prefecture, the lack of fast transport meant limited access to modern healthcare, education, and economic markets. The region remained a beautiful but impoverished island in the sky. China's national strategy for the Great Western Development demanded a solution that could bypass these mountains entirely. However, the geography made traditional solutions impossible. Building a high-speed railway across these vertical gradients would have cost 10 times the national average and taken decades to complete. Tunnels would have to be drilled through unstable, frozen rock at extreme altitudes. This left the Chinese government with only one radical option. They had to go over the mountains. But building an airport at 4,411 meters wasn't just a logistical challenge. It was a declaration of war against geography. The goal was clear: to turn a 48-hour nightmare into a 1-hour flight, effectively shrinking the province and integrating the Himalayas into the modern Chinese economy. But to achieve this, they had to build a facility in a place where the air is too thin to breathe comfortably and where the very machines needed for construction would struggle to function. In the world of aviation, altitude is usually a pilot's friend until you have to land in it. At Daocheng Yading, the primary adversary isn't the rugged terrain or the freezing wind, it is the physics of the air itself. To understand why this airport is an engineering anomaly, we have to look at air density. At sea level, air is thick and packed with oxygen, providing the lift wings need to fly and the breath engines need to burn fuel. But at 4,411 meters, the atmosphere is 40% thinner. This thin air changes everything we know about how an airplane behaves. The first casualty of high altitude is engine performance. A jet engine is essentially a massive air pump. In the thin Himalayan atmosphere, the turbines draw in far fewer air molecules, which means they produce significantly less thrust. It's like trying to run a marathon while breathing through a straw. Because the engines are suffocating, the aircraft cannot accelerate as quickly as it would in London or New York. To reach the necessary speed for liftoff, the plane needs much more runway. This leads us to the airport's most striking feature, its runway. Stretching a massive 4,200 meters, it is one of the longest commercial runways on the planet. You might expect a runway this long at an airport that handles the massive Airbus A380, but here, it's a necessity for much smaller planes like the A319 or Boeing 737. The physics tax is so high that even these medium-sized jets require every extra meter to safely get off the ground. But taking off is only half the battle. Landing at this altitude is equally dangerous. Thin air means there is less aerodynamic drag to slow the plane down as it approaches the tarmac. Consequently, planes must land at much higher ground speeds than normal. This puts immense pressure on the aircraft's braking systems and tires. At Daocheng, the landing isn't a gentle descent, it's a high-speed calculated impact where the pilot has very little margin for error. If the brakes fail or the thrust reversers don't engage instantly, the aircraft could easily overshoot even a 4-kilometer runway. There is also the weight penalty. To operate safely in this thin air, planes often cannot fly at full capacity. Every extra kilogram, whether it's luggage, fuel, or passengers, makes the takeoff more dangerous. This means that even if a plane has 150 seats, it might only be allowed to carry 100 passengers to ensure it is light enough to climb over the surrounding peaks. Pilots also have to deal with true airspeed variations. Their instruments might show one speed, but they are actually moving much faster across the ground than they realize. Engineering a solution for these physical constraints wasn't just about pouring more concrete. It required a complete recalibration of flight software and specialized training for crews. At Daocheng Yachting, the invisible enemy of thin air dictates the length of the runway, the weight of the suitcases, and the very design of the engines. It is a place where human ingenuity has to compensate for the fact that, according to the laws of physics, planes shouldn't really be here. Building the world's highest airport wasn't just a construction project. It was a 24-month war against a hostile environment. In 2011, when the first teams arrived on the plateau, they faced a landscape of jagged granite and permafrost soil that stays frozen year-round. The first major hurdle was the machinery itself. Standard bulldozers and excavators are designed for sea-level oxygen. At 4,411 meters, their internal combustion engines choked, losing nearly half of their horsepower. Engineers had to bring in specialized, high-altitude tuned equipment, essentially giving the machines turbochargers just so they could breathe. Then came the concrete crisis. To build a 4,200-meter runway that could support 100-ton jets, you need massive amounts of concrete. But on the Tibetan Plateau, temperatures can plummet below freezing even in the middle of a summer night. If the water in the concrete freezes before it sets, the entire runway becomes brittle and useless. The solution was a sophisticated chemical cocktail of anti-freeze additives and accelerators, combined with thermal blankets to keep the beating heart of the runway warm during the curing process. It was a race against the clock. Pour, treat, and cover before the Himalayan frost could destroy the work. But the most fragile components on the site weren't the machines, they were the humans. Every breath at this altitude contains 40% less oxygen. Construction workers faced debilitating altitude sickness, severe headaches, and extreme fatigue. To keep the project moving at its lightning-fast pace, the Chinese government implemented a military-grade rotation system. Specialized medical teams were stationed 24/7 on site, and every worker was equipped with portable oxygen canisters as part of their standard uniform. Despite these brutal conditions, the project moved with a speed that shocked global observers. In less than 30 months, the mountains were leveled, the permafrost was conquered, and the runway was laid. By September 2013, the impossible was finished. China hadn't just built an airport, they had successfully conducted a massive logistical experiment in one of the most uninhabitable places on Earth. When travelers first catch a glimpse of the Daocheng Yachting Terminal, they often feel like they've stepped into a science fiction movie. Rising from the desolate gray plateau is a sleek, silver disc-shaped structure that locals have nicknamed the Flying Saucer. But this isn't just an aesthetic choice to impress tourists, it is a masterclass in physiological architecture. In an environment where the very air can kill your energy, every curve and corridor of this building was designed to solve a medical problem. The architects drew inspiration from the kata, the traditional Tibetan ceremonial scarf that symbolizes purity and welcome. But beyond the cultural symbolism, the circular, non-linear design serves a critical functional purpose, minimizing walking distances. At 4,411 meters, even walking 50 extra meters can cause a passenger's heart rate to spike and their oxygen levels to drop. By creating a centralized, compact hub, the design ensures that passengers spend the least amount of physical effort possible to get from the gate to the exit. It is a building designed for people who are, quite literally, out of breath. The real magic, however, happens inside the walls. The terminal functions like a pressurized space station. Because the external atmosphere is so thin, the building is equipped with a sophisticated, large-scale integrated oxygen enrichment system. As you walk through the lounge, you aren't just breathing the mountain air, you are breathing a specially filtered mix that brings the effective altitude inside the building down to a manageable level. There are dedicated oxygen bars and emergency medical pods located every few meters, ensuring that if a traveler suddenly succumbs to acute mountain sickness, help and air is only a step away. Another hidden challenge of the Himalayas is the cognitive fog caused by hypoxia. When the brain lacks oxygen, people become confused and disoriented. To counter this, the interior design utilizes high-contrast wayfinding. The lighting is ultra-bright and the signage is simplified with bold colors and massive icons. The use of natural light is maximized through giant, reinforced glass panels that offer 360-degree views of the surrounding peaks. This isn't just for the view, it helps the brain stay grounded and oriented by keeping the horizon visible at all times. The glass itself is a marvel, treated with multiple layers to block the intense high-altitude ultraviolet radiation while retaining internal heat. Even the materials were chosen for their thermal intelligence. The silver metallic skin of the saucer isn't just for show, it's a high-tech shield that reflects the harsh daytime sun, while acting as a massive insulator during the brutal Himalayan nights. The terminal is a closed-loop environment designed to maintain a stable, humidified, and oxygenated atmosphere regardless of the chaos outside. At Daoqing Yachting, the architecture doesn't just house the travelers, it keeps them alive. It is the bridge between the hostile reality of the Tibetan Plateau and the biological needs of the human body, a silver sanctuary in a land of rock and ice. Flying into Daoqing Yachting is not a task for the average pilot. It is a specialized mission that requires high-altitude certification. Because the air is so thin, the margin for error evaporates. Pilots must wear oxygen masks during takeoff and landing, not just as a precaution, but to ensure total mental clarity during the most critical seconds of the flight. The operational rules here are ironclad. Most flights are restricted to the morning hours because by afternoon, the Himalayan winds become too turbulent and the weather too unpredictable. There is no instrument landing system that can overcome these peaks. It is a visual battle. Pilots must navigate terrain-hugging flight paths, often flying at less than full capacity to ensure they have the climb rate needed to clear the surrounding 5,000-meter ridges. One wrong calculation in airspeed or a slight delay in engine response, and the mountain wins. At Daoqing, every landing is a testament to the perfect synchronization between advanced Chinese avionics and the nerves of steel possessed by the pilots who brave the roof of the world. Building a sanctuary in the sky comes with a heavy price tag, and not just in currency. While the $255 million investment seems modest for such a feat, the true cost is measured in the impact on this fragile ecosystem. The Yachting Nature Reserve, often called the Last Shangri-La, now faces a double-edged sword. On one hand, the airport has breathed life into the local economy, turning a 48-hour trek into a surge of tourism that supports thousands of Tibetan families through new hotels and services. But on the other hand, the instant access to the Himalayas threatens the very silence that makes it holy. The rapid influx of thousands of daily visitors puts immense pressure on local resources and ancient cultural traditions. There's also the environmental footprint. High-altitude emissions are more damaging to the atmosphere, and the expansion of infrastructure risks scarring the pristine landscape forever. China's Great Western Development has successfully erased the distance, but it has also triggered a race against time to save the soul of the mountains from the weight of their own success. Daoqing Yachting is more than just a destination. It is a laboratory at the edge of the world. By conquering the forbidden zone of the Himalayas, China has rewritten the handbook on high-altitude aviation. This airport now serves as the ultimate proving ground for the next generation of aircraft. If a plane can perform here, it can perform anywhere. It is a testament to the fact that for modern engineering, there are no unreachable places, only challenges waiting for a solution. What started as a desperate attempt to bridge a 48-hour gap has become a symbol of 21st century ambition. Daoqing yachting proves that we can breathe life into the thinnest air and build sanctuaries where none should exist. As the silver flying saucer glows against the Himalayan peaks, it stands as a reminder. We are no longer bound by the geography we were born into. We are now a species that can build its own gateways to the stars, even on the roof of the world. There are places on Earth where engineers quietly agree on one rule: you simply don't build there. Not because it's impossible in theory, but because failure would be unforgiving. The Yarlung-Tsangpo River is one of those places. It cuts through the eastern edge of the Himalayas, flowing across active fault lines, unstable mountains, and terrain shaped by geological forces that are still moving today. For decades, engineers looked at this river and reached the same conclusion. The risk outweighed the reward, but that conclusion is now being challenged. China is planning a massive hydropower project in this exact location, a place where a single miscalculation doesn't just mean delays or cost overruns, but consequences that can't be undone. So why build here at all? How do you design infrastructure for a landscape that refuses to stay still? This is not a story about scale alone. It's about risk, decision-making, and how modern engineering confronts uncertainty. This video isn't asking whether the project is impressive. It asks 4 engineering questions. Why attempt to build a massive hydropower system here at all? How is it even supposed to work in such an unstable environment? What are the failure modes engineers fear the most? And finally, is the payoff worth the long-term risk? To answer those questions, we need to start with the river itself. From an engineering perspective, the Yarlung-Tsangpo represents an uncomfortable truth. It may be one of the most energy-dense rivers on Earth. In its lower reaches, the river drops hundreds of meters over a relatively short distance. That drop translates directly into gravitational potential energy, the raw fuel of hydropower. On paper, the numbers are staggering. A single stretch of this river could theoretically generate more electricity than many large dams combined. For China, the motivation is not mysterious. Electricity demand continues to rise. Coal remains reliable but costly, economically and environmentally. Wind and solar are expanding rapidly, but their output is intermittent. Hydropower, when it works, offers something rare: stable, dispatchable, long-term renewable energy. But there's a deeper layer to the decision. Energy generation in China is geographically mismatched. Demand is concentrated in the east. The largest untapped energy resources lie in the west. That creates a persistent engineering problem: how to generate power where people don't live and move it reliably to where they do. In that context, the Yarlung-Tsangpo isn't chosen because it's safe. It's chosen because it's efficient. And efficiency in engineering often comes with uncomfortable trade-offs. If the potential is so extraordinary, a logical question follows. Why hasn't anyone built here before? The answer lies in the environment. This region sits near active tectonic boundaries. Earthquakes here are not rare events. They are expected features of the landscape. The mountains themselves are young and restless, shaped by ongoing geological forces. Rock layers are fractured, slopes are unstable, landslides are common. Then there's the river. Seasonal flow variations are extreme. During flood periods, water volumes increase dramatically, turning construction windows into narrow, high-risk opportunities. And finally, there's logistics. High altitude means low oxygen. Low oxygen affects workers, machinery, and productivity. Every ton of concrete, every turbine component, every piece of equipment must be transported into one of the most challenging construction environments on Earth. Traditional hydropower models, massive concrete dams relying on geological stability, simply don't translate well here, which is why this project's not trying to repeat the past. It's attempting a different approach. Despite popular headlines, this project is not expected to rely on a single river-blocking megadam. Instead, the design philosophy appears to favor a diversion-based system. Rather than stopping the river, engineers aim to redirect part of its flow. Water would enter long tunnels carved deep into the mountains, travel through underground passages, and drive turbines housed in massive subterranean caverns. The river itself continues downstream. From an engineering standpoint, this approach offers several advantages. First, it reduces surface disruption. Second, it avoids concentrating pressure behind one enormous structure. And third, it allows the system to be divided into multiple components rather than a single point of failure. In simple terms, the design doesn't try to overpower the river. It tries to coexist with it. But this introduces new challenges. Tunnel-based systems demand extraordinary precision. Turbines require millimeter-level alignment. Water flow must be controlled across long distances without inducing destructive vibrations or pressure surges. And all of this happens underground, inside rock that may shift slowly over decades. This is no longer just civil engineering, it becomes long-term geological management. This is where the project moves from ambitious to brutal. Engineers don't ask whether a system can fail, they ask how it fails. And here the failure paths are complex. Seismic risk. This is not a question of resisting earthquakes, it's about surviving them. A sudden fault movement doesn't need to destroy a structure outright to cause catastrophe. A shift of just a few centimeters can misalign tunnels or damage turbine systems designed with extremely tight tolerances. Long tunnels through fractured rock face constant threats: rock bursts, water ingress, and gradual deformation. A collapse wouldn't simply stop power generation. It could trap water, increase internal pressure, and cascade into adjacent sections of the system. Long-term geological movement, mountains move slowly, but relentlessly. Over decades, small movements accumulate. Stress builds, materials fatigue. The challenge isn't predicting tomorrow's conditions, it's designing for changes no model can fully simulate over a century-long lifespan. Construction reality. Even before operation begins, the construction phase itself is hazardous. Short weather windows, reduced human endurance at altitude, complex coordination between surface and underground teams. At this scale, delays aren't just expensive, they're dangerous. So, is it worth it? Supporters point to the benefits. Massive clean energy output, reduced reliance on fossil fuels, long-term strategic energy security. Critics focus on what can't be undone: ecological disruption, downstream uncertainty, maintenance costs that may grow faster than projected. And this is where engineering judgment becomes essential. The hardest part of any mega project isn't building it. It's operating it safely for the next 50 to 100 years, in an environment that constantly challenges your assumptions. The real cost of infrastructure is paid long after the opening ceremony. The Yarlung-Changpo Hydropower project is more than an engineering proposal. It's a test of how modern infrastructure responds to uncertainty. If it succeeds, it may redefine what's possible in hydropower. If it fails, the consequences won't be symbolic. They'll be geological, environmental, and irreversible. So the question isn't whether this project is impressive. The question is, when engineering reaches this far into the unknown, how confident do you need to be before you begin? When projects reach this scale, success is no longer defined by whether construction is completed. It's defined by what happens after. After the headlines fade, after the ribbon is cut, after the first decade of operation reveals which assumptions were correct and which ones quietly weren't. The Yarlung-Changpo hydropower project sits at the edge of what modern engineering believes it can manage. Not because engineers lack skill, but because nature here refuses to behave predictably. If the system performs as intended, it may become a benchmark for how extreme environments can be harnessed without being overwhelmed. But if the balance tips even slightly, if geological forces move faster than designs anticipate, the consequences won't arrive suddenly. They'll accumulate, silently, over years. And that is what makes this project truly extraordinary. Not its size, not its power output, but the fact that it asks engineers to commit, not just to construction, but to decades of vigilance in one of the most unforgiving landscapes on Earth. So the question this project leaves us with is not whether it can be built, it's whether humanity is prepared to take responsibility for infrastructure that will be tested every single day by forces far older than engineering itself. So the real question isn't whether this project can be built, it's whether we're ready to live with the consequences decades after construction ends. If you want to understand how engineering decisions shape the future, subscribe to the channel. Thank you for watching. See you in the next video.